老师好，老师好，请问可以听得见吗？
喂，我可以听到。
对对对，今天是那个彭老师做主持，然后就是我和另外一个 assistant 两个人会把他们直播间的，如果有一些问题的话，我们会发到那个聊天框那里，然后你可以看一下。对，
嗯，好的，
好的，
好的，
谢谢。
谢谢。
如果是没有的话，可能需要彭老师准备一些问题，然后问一下
好嘞，
两位嘉宾，好吧？这样子。
好嘞。嗯，
然后我们是7点钟开始，然后第一个讲的老师，我不知道是谁啊，可能是
是刘
是我，是我，
洋老师。
哎，是我，
哦
哎，
，OK，好好好，那么我们就7点钟准时开始就可以了，就这样子。行，如果有什么不懂的话，你可以私聊我跟另外一个助理。对，OK，
好好辛苦辛苦，哎，
好好好。
好，哎，斯达，哎
刘老师您好。
哎，那个
嗯，
待会儿是我讲完了，咱们就直接是 Q&A 是吧？然后
对，
我不等，就是下一位那个讲者，我就不用等着他讲完吧，是吧？
不用，不用。
我就退出。哦，OK OK，
嗯，
行行，好，我看看。
刘老师好，刘老师可以听得见吗？对。
对，我这边可以听到的，你们可以让
对对对，
我知道。
然
嗯
后这边的话是那个哦，就另外一位刘老师先讲，
啊，
刘洋老师先讲，
啊
对对
你好，对，
对，然后讲完之后才可以才轮到刘老师你讲，对对，
好，没问题，好的，
行行好。
嗯
嗯，OK。Hello everyone. Welcome to our online webinar. Today, our topic is about 3D generation. It's honor to have Yang Liu and Ziwei Liu for presenting their great work and insights. The first speaker is Yang Liu. Okay, let's introduce Yang Liu. He is a principal researcher at Micro Research Asia. His research interests include 3D modeling, geometry processing, and 3D vision, with a recent focus on a learning-based 3D processing, understanding, and generation. Dr. Liu has been an editor board member of for Talk and TVCG. Okay, Now let's welcome Yang Liu for starting his talk.
Okay, thanks for Siddharth's introduction. So let me share my screen. Share. You need to allow me to share this meeting. I cannot share the screen right now. Who is the host? So you need to enable the sharing function for me. Currently, I cannot share the screen because it says sharing is not turned on.
Can assistants help this?
Okay, just wait for a moment. Yeah. Okay, I think there's something changed. Yeah, let me try again. No, still doesn't work. Mm.
Maybe we restart the Zoom can solve this problem.
Oh, I can share screen right now. I think I
Okay.
have the functions enabled. Let me share my screen. Can you see my screen?
No, it's black. Oh, okay. Now I can see your screen.
Yeah, just use some delay. Okay, so let me start. Yeah. Okay. Hopefully my computer will not crash. Sometimes it crash. Yeah. Okay. So my so the topic I want to yeah, talk about is about scaling up the data for enhancing 3D learning and generation. So why I choose this topic? So I got some motivation. Yeah. So just briefly introduce my motivation. So the reason I chose this topic can be attributed to our previous research in 3D learning. So in recent years, we have developed effective learning frameworks such as oak tree-based CNN, called OCN, and we also explored various methods in supervised, unsupervised, and semi-supervised 3D training and pre-training. And recently, we also conducted a series study on learning-based 3D reconstruction, modeling, and generation. Okay, so after we done all this research, so we got some lessons from our this as a research journey. So one significant lesson is that the scale of the 3D data really matters for 3D learning. So I'm sure many of you share the same experience. Yeah. For instance, the main technique we developed for that work for the small data sets such as ModelNet or ShapeNet very well, but may not work for the large 3D data set. So our students also often frustrated about this approach. Yeah, so we invent some new stuff and it doesn't work. Yeah, especially we just move to these techniques to the large data set. However, the good news is that with the large data set, we can simplify and enhance our network design. So another important point is the shortage of a large 3D data set, especially for those that are with high quality and well labeled. So when we start our some 3D learning project, the first question is, where are the large data set for our learning? So we need some large data set to prove our design, or also to maximize our research value. Okay, and once we have this, we got some large data set from website, from other website, or we created them by ourselves. We need to think about how to utilize this large data set. Whether it's very simple to utilize them, or there's also we need another kind of processing to make this data set really useful for our 3D learning or 3D generation. So in this talk, I will briefly introduce our two projects to showcase how we utilize a large data set, how we scale up the data, and also develop the network to make this large data set really useful for 3D learning and for 3D generation. So the first topic is about 3D pre-training. So we developed two kind of a backbone structure called Swing 3D and the Swing 3D++. Okay, let's see the first project. So well, I need to give some background about the 3D pre-training. So actually, in recent years, we have seen the paradigm shift in NLP and the 2D vision. So we can see that with the many large pre-trained backbones have achieved significant success in the NLP and the vision domain. And it's also widely recognized that the effectiveness of these pre-trained models is greatly influenced by the scale of the state site and the model size, known as scaling laws. So for 3D, yeah, actually, we also have seen a series of 3D pre-training work published in recent years, aiming to replicate the success achieved in NLP and computer vision domains. So very many approaches have been explored, and many focus on the learning schemes, such as whether we're using the generative approach or using some reconstruction-based loss function, something like that. So however, the model scalability has been less studied in past maybe 2 years, but recently there's more work. Yeah. The reason is this work, model scalability have been less studied is mainly because I think it's lack of large 3D data set. And so we start to think about how to develop a scalable 3D backbone and backbone for 3D learning. Yeah. So we have some observation and also found some opportunity on this direction. So actually 2 years ago, we observed that the popular sparse convolution-based backbone is just like our OCNN, lacks capabilities due to their limited perception field. Yeah, although there are some study use a large convolutional kernel, so they can expand the reception field, but the potential for 3D learning still remained unexplored. But in recent years, we also see that pre-trained backbone design in LP and CB has converged to some transformer backbones. We can, for instance, in computer vision, we have seen swing transformer has shown this it's very powerful and also scalable for large data set. So this gives us our hints. So transformer backbone should be quite useful for 3D learning. So nowadays there's many papers are using transformer already. Yeah. And another observation is we don't have the large scale real data for 3D training. So several years ago, if we just checked all the 3D learning paper, we're just using some ModelNet, ShapeNet. Also, we have some ScanNet paper, ScanNet dataset for use, and or using the Matplotlib 3D. So we can see the data scale is still limited. And recently, we have seen many other 3D dataset has emerged and with larger scale. For instance, in our project we use a Stretch 3D. Actually, it has 10 times larger than the ScanNet dataset. And for the 3D generation, we have seen a lot of approach using Observerse, Observerse XL. It's a large dataset for getting the better generation result. Also, our next speaker also create some nice real scan object. I think it's currently the largest real scan object. So people also using this tool for different purposes. So we would like to utilize some large data like the Structure 3D for designing and validating our 3D pre-training backbones. So our goal actually is quite straightforward. So we try to develop a scalable, efficient, and generalizable 3D pre-training backbone for 3D understanding. Currently meaning for the 3D perception, not for 3D generation for this project. So we hope to see some significant performance improvement as the model size and the pre-training data size increase. So our backbone design is actually inspired by the Vision transformer, swing transformer, which is a hierarchical and windows-based transformer that applies self-tension across both regular and shift 2D windows in a multi-scale manner. Yeah, it has demonstrated high efficiency and scalability. So we try to make it work for the 3D. But the question is, it's really trivial to extend the swings transformer to 3D. Oh, sorry, it's a typo, to 3D. Yeah. So unfortunately, we identified two serious issues. The first issue is the huge memory cost. So actually, if we just discrete the 3D into some regular windows, so for each 3D windows, so there's about OM squared non-empty voxels. Yeah. So if we apply vanilla self-attention, we would require the force power of M the storage actually is quite large. If we consider that there's a large number of the windows, 3D windows in the 3D things. So the memory cost we cannot afford in general. Yeah. And the second issue is we noticed the 3D data actually presents the highly irregular signal variations. So signal variation, including the point position and point normal, point color, such as within a small 3D windows, actually the change of the point position, normal colors, especially normal and color could be quite large. So, but this change had not been considered by 2D transformer design because in 2D there's no such large variations except for the color. Yeah. So we propose two key designs to address these issues. The first designs we call this memory efficient self-attention mechanism. So actually it rewrites the vanilla self-attention formula very simple in a simple way. So we can write it in the right sorry, I can, okay. Yeah, you can see this formula. We just rewrite this vanilla self-attention formula to this formula. And we can compute the denominator and the numerator in parallel. And we don't need to store very large tensor matrix about the EIJ and the alpha IJ. And in this way, we can reduce the GPU memory to linear cost without sacrificing attention accuracy and the computation speed. Okay. So this is our first key design. The second key design is called contextual relative signal encoding. Actually, the original idea is from the another two papers. They have just bring the relative position encoding to both query attention queries and keys, enhance the transformers capability. So in these papers, in their papers, the relative position encoding is just about the point position. So we extend them by incorporating the positional, normal, and color difference into the 3D transformer, just into our 3D swing 3D transformer. Here, delta Sij represent difference vector between two points within a window, a 3D windows. And the TK, TQ, TB are learnable mappings that provide contextual information to the original attention formula. In our implementation, with this TK, TQ, TV actually is a learnable lookup tables that maps the contextualize the positional or signal changes to the feature space. Yeah. For more details, maybe you can check our paper. Yeah. So with this two key design, we just develop our backbone structure. It's called Swing 3D, and we can see that the whole pipeline is similar to a Swing 2D. Yeah. So our Swing 3D contains four key modules. Yeah. The first is the voxelization module transforms the input point cloud into a sparse voxel grid. Next, the initial feature embedding module generates a sparse voxel feature for self-attention computation. And the Swing 3D block then perform memory efficient self-attentions on these features using within the regular and the shift 3D windows. Lastly, the down sample module just compares all the feature for subsequent level. And together, this module just make our 3D Swing 3D powerful encoder, and we can use it adaptable to various 3D applications with compatible decoder that we can use for the different applications. This is our design. So now let's switch back to the large data. So with our transform design, so we just try to pre-train it with a large data set that we mentioned before. That is called the Stretch 3D. As Stretch 3D has contains 21,000 rooms and is one of the largest in ScanNet. Although it's synthetic data, actually it provides very good photorealistic rendering qualities. And unfortunately, this dataset only provides some render images, so we just reproject all this image to 3D to get the point cloud. And we're using the point cloud, the colored point cloud as our training data, and for pre-training our Swing 3D encoder. And we can specify different feature channel and head numbers. So we construct two versions of the Swing 3D, a small model and a large model. So both are memory efficient on GPU and exhibit high time efficiency. And for pre-training this task, we actually performed supervised pre-training, and we're using the semantic segmentation as our pre-task because the dataset itself has provides a per point label, so we can do the supervised training. So actually, our data structure, our network structure can support the unsupervised training, but we didn't perform this training in our work. Okay, so actually we accessed our model efficiency by comparing it with another transformer. It's called stratified transformer. It's the early version that extended the Swing 2D to 3D. Yeah, and also our vanilla version of the Swing S and our more efficient version based on Swing S. So we can see this from the table. So our efficient version actually incurs significantly lower cost, especially in memory consumption, which is 1 order of magnitude smaller than the stratified transformer. Okay, we also access the scalability of Swing 3D on various data scales just by altering the pre-training data ratios. So these plots demonstrate that the Swing 3D S performance actually is improves with the increase in pre-trained data set. You can see we just changed the training data ratio from 10% to 33% and to 100%. You can see the improvement about this performance. And we also compare the other backbone, like the transformer, like the point transformer V2. It's a transformer-based based backbone, and also another sparse convolution-based backbone. We can see for the point transformer V2 and the sparse convolution, the benefit from this training data is actually limited. Yeah, it's and we also assess the scalability of our Swing 3D with respect to the model size. So we can see from this plot, yeah, the Swing 3D L, the red curve, yeah, benefit from the increase in model size. Additionally, we also dropped the contextual relative signal encoding and they discovered it. It's actually this design is quite important to the model scalability. So from the right figure, we can see without this kind of CRSE encoding, the performance drops even for the large model. Yeah. So it means our position contextual relative signal encoding captures more how to say more subtle changes within a window. So the transformer can capture this change and to get a better performance. Yeah. So with pre-training, so our Swing 3D actually exhibits a significantly better performance than previous works on various tasks, such as 3D semantic segmentation on ScanNet, on S3D IS. Yeah. So, so we also found that this performance improvement on the 3D detection tasks. So you can see we just combined our pre-training encoder with some state-of-art 3D detection framework. We can see using the pre-training, so the performance increased significantly. So we further validate the importance of using the large data for pre-training. So our downstream stacks is semantic segmentation on S3DIS, which use the real capture data. So here we can see we just switch the pre-training data set from structured 3D to ScanNet. We can see although the ScanNet data is also real data, real capture data, but the scale of this data is quite is limited, compared to the structured 3D. So even for the structured 3D is a synthetic data, so the performance is quite significant. So from this one, we see the importance to have a large data set for training. Yeah. Now, from the above experience, it appears we can use the large data set is important for the pre-training. That's we have a naive ideas. So whether we can combine all the available 3D data set for pre-training. Yes, in that way we can increase the data size more significantly. So, but does this work? Our answer is no. So if we merely feeding the different 3D data set into the pre-training, it's ineffective. So here's look at this table. So you can see if we just using the multi-source data, we just combine StressD and ScanNet for pre-training and perform the downstream task on ScanNet segmentation, we can see the performance actually drops. So what's the reason? Yeah. So we need to dig out more about this behavior. So first we check the difference in this data source. We can see the capture device actually different, even for the ScanNet and the S3DIS. One of using the structural sensor and another using the multiple camera. And the the things type also have some variations. Okay, so this factor could cause domain gaps among these data sets. So it means we cannot directly combine this data without any processing. Yeah. So we also analyze the domain gap between the different 3D data using the H divergence technique. This technique actually using the trained classifier to assess how distinguishable two data sets are. So I have list this equation. Actually, it's simple. We just train some network and called H, and we just to check the error rate between the different data set. So here we have 3 experiments. So we can compare the domain gap between the ScanNet and Stretch 3D. So the score is near to 2. So actually, the large value means a large domain gap. So we can see both this combination actually lead to a large domain gap. Yeah, it means we can it means even for the ScanNet and the 3ds they are capture their real data, we cannot combine them together simply. Yeah, for pre-training. We also analyze the Windows sparsity, the variance of the point position, color, and normal within a fixed size windows. So we just crop a point cloud windows and to count the number of number of non-empty voxels and also other signal variations. So from these curves, actually we plot the normalized cubic histogram of all these quantities. We can see for different data sets, you can see the curve actually are not close to each other. So it means there's a significant gap between among these data sets. So we need to deal with them carefully. So to best utilize multiple 3D dataset for training and resolve these domain gaps, we propose an enhanced network structure. It called Swing 3D++. So actually, compared to Swing 3D, that it includes a set of domain-specific modules. So you can see, I just highlight these modules. So you can see which for the sparse cone, we switch to the domain-specific sparse cone. And for the BN, we have a domain-specific BN, and also we have other domain-specific designs. So the key idea actually is to ensure that all these module can handle domain gaps. Yeah. So while the project tensor like QKV for the attention computations remain shareable across different datasets to reflect a common data prior, but for the domain-specific modules, to each dataset has its own parameters, but it's also lightweight. Yeah. So there's a few key design of Swing 3D++. So I just want to mention 3 of them. Yeah, due to the time limit. So first one we call the domain-specific voxel promotes. Yeah. So actually we noticed that if a 3D window contains very few points, the prediction accuracy is very low at this point. So to address these issues, we introduce a small number of virtual voxels into each windows. The feature on these voxels actually are learnable and shared across windows, but distinct between different datasets. This strategy is called domain-specific voxel promotes. So after we adding this virtual voxel promotes, actually we can improve the prediction accuracy for the Windows, for the original Windows with less number of points. Okay. Actually, this formula we also need to revise our attention formula, but actually it's simple. You can see we just insert a few more voxel features into the attention computations. So we just skip this page. And another key design is to replace our original contextual relative signal encoding with a more capable version, which we call VM CIC. Actually, it uses a vector metric decomposition to encode the 3D relative changes. So for each dataset, we also did. So we can see if people are familiar with the TensorIF work, we can see that some feature can be a 3D volume feature can be decomposed to the vector and the metric, and to reduce the storage. Also, we can have a better, good approximation quality to the original feature volume. So we are using the similar ideas. So here's just the formula. You can see like this. The first one is 1D table. We actually implement as a 1D table, and the second one is the 2D table. Yeah. And for each dataset, we also modulate this VM CIC with a lightweight VM multiplier. You can see the last equations. The red one actually is a domain specific parameters, and the black ones are just shared parameters. So in this way, our CIC are domain aware, and also we also shared some large parameters across different data set. So that another strategy is called the source augmentation. Actually, it's quite simple. So we augment each data set just by dropping some signal types, such as point color, or point normals, and treat it as a new data set. So this strategy actually enrich the data scale and the signal types various for free. Yeah, we found that, for instance, for giving us one data set, we can create 4 data sets. And we found all this augmentation actually improved our pre-training. Yeah. So our final backbone is built upon 3D Swing 3ds with lightweight domain-specific parameters. So actually, the increase the parameters compared to Swing 3ds is due to the large shared parameter of the VMCIC. And once pre-trained, for downstream tasks, we only need to load the shared weights and the domain-specific weights of one pre-trained dataset that could be close to the downstream task dataset, and we perform the fine-tuning. So we also did a thorough ablation study to prove the effectiveness of each introduced module. So here we did some appreciation about our modules, like the MS means using the multi-source data, and SA is such SA is used for source augmentation, and the domain DM CIC means the domain modulator. We can see from this table, we can see when we add this module, gradually we can see the performance on the downstream tasks increase. Yeah. Of course, we need to compare our result with other approaches. Okay. Actually, you can see after pre-training, so our Swing 3D plus which pre-trained on just on 2 dataset outperforms other method. This includes the point transform point V2 and the PPT, which although pre-trained with the 3 dataset, but they didn't consider domain gap. So their performance is lower than ours. And for 3D detection, actually our multiple source pre-trained Swing 3D plus also achieved the best performance. Okay, we also found the Swing 3D plus can be quite useful for the data efficient learning. So in this case, the downstream dataset, training dataset is quite limited. So for this case, we only need to fine tune our domain specific parameters. So we just fix all the large shared parameters and fine tune the lightweight parameters. And we can see when for the ScanNet 200 segmentation, when the data ratio is about 1%, 5%, our strategy is much better than fine tuning all the parameters and other approaches. Yeah. Okay. That's our journey on this pre-training. Utilizes the large data set and all developing the transformer-based backbone. The next project is about 3D generation. So let's see how we can leverage large data to make the model scalable and more effective. Okay. So actually recently we have been studying 3D indoor scenes generation, using the in the wide image data. So why we're using in the wide image data? So actually our project goal is quite straightforward. we want to generate a realistic room-level indoor scenes with coherent semantics and rich context. Yeah, here's just a inspection video, yeah, showcasing the quality we aim to achieve. It's not our result. I just put here to see the final goal, what it should be look like. Yeah, currently we are still far from this quality. Yeah. Okay, so when we're starting this project, we need to look at the existing 3D indoor dataset and see whether we can use them. So here, I just list the table and show some typical dataset. We can see, although there are some good dataset, but actually compared to the image and also the language dataset, the 3D indoor dataset actually it's still quite small. Yeah, quite small. So although there are some good research efforts utilize this 3D dataset, yeah, for instance, the popular 3D front dataset has been being used for many diffusion-based or autoregressive-based works, but we still feel they don't cover enough the sorry. They are still not sufficient to cover the diversity and the richness of the real indoor scenes. Yeah, because they are synthetic room, many are synthetic room, and the room also looks too clean. Yeah, actually, we want to model some disorder or the chaos of the real things. So we just we examined the image data set. Actually, we found the scale of the image indoor image is quite huge. So for instance, the L sound data set contains millions of indoor image. So can we build a 3D generation model and let the rendered image can match the distribution of this in the wide image? Yeah, if we can do that, so we can get the good 3D generation model. That's our original motivation. So, however, as this in the wide image are unlabeled, we faced several data challenges. First is the global camera pose are unknown. Yeah, making it hard to align the indoor image within a global consistent coordinate system. Second, the camera pose distribution actually is unknown and uneven. So as the indoor photo, are taken by human, don't follow the uniform sampling. So we cannot just make a assumption about the camera pose randomly sampled in the room. And so for a 3D general model, which we want it to match the distribution of the render image with the training image, we need to know where to take the photos. So we need to get some information about the camera pose info distribution. Yeah. And thirdly, we actually lack the global 3D layout information. We just have images. We cannot have the complete 3D scenes for super region. So to overcome this challenge, we propose two key designs. First, we build a local coordinate system, yeah, to align the training image in a local way. And we call this strategy is local pose alignment (LPA). And with this LPA, we'll actually design a GAN model called the LPA GAN, which simultaneously synthesize the room level 3D scenes in nerve representation and reconstructs a camera pose under the local coordinate system and also sample the camera pose that matches the distribution of the training dataset. This is our two key ideas. So I will introduce them one by one. So what's the local pose alignment? So actually we create this term by the inspiration. What kind of inspiration? So we can see the human can rapidly estimate the rough camera pose from distinctive room objects and the structures, and from the spatial relationship of these objects from just for single image. So based on this inspiration, so actually we for each room type, for instance, the bedroom, so we can define a core object representing the room's main function. For instance, the bed is the core object in a bedroom. So we assume the bed location or orientation is known. So we can order the things corners. For instance, if the things is a square room, yeah, we can order the four corner in order. So we know which one is first the corner and second corner because they are all respect to this the core object. So for a bedroom image, once a bed is identified, the room corners shown in the image can be ordered. So in this way, we can then build a local coordinate system just by treating the corner as the origin, and with the bed front right direction as the x and y axis, and the z axis just point upward. Yeah. So actually, we for the indoor for this room image, bedroom image, actually we can define the 4 types of local system because we have 4 corner. So once we have this local system, so for each image, its camera pose we can define using this under this local coordinate system. So it's includes the anchor type. So we have 4 types. So 1, 2, 3, 4, and the local transformation about this camera pose, a camera, and also the rotation angle about the camera and the field of view. So actually it's 8 dimensional vector to define this local camera pose. And in practice, we actually don't need to know the exact local transformation, rotation angle, and field of view for the training data because we don't have this knowledge. But we can classify the anchor type easily. So we actually design a classification network and label a small data set for learning this anchor type. So in this way, in the wide image, we using this classification network, we can classify each image into a one of the 4 groups because we only have the 4 types of this corner. Then we feed all this information to our LPA GAN framework, and then we can use it to generate the 3D nerve, and then we can use it to render the different view, the sex, to get the 3D results, also the rendering results. So here we would like to illustrate the LPA GAN model, which contains the 3 learnable networks modules. The first is generator, which takes a random noise or other condition input like the room size, and to output 3D things in triplan-based nerve interpretation. The discriminator distinguish between the render image of generated things and the real image, and the camera pose predictor estimates the local camera pose of the input image. So giving the known anchor type. The anchor type means the corner, which corner we have a detector for this image. So the training process actually contains the 2 main alternating steps. The first step is we can frozen the camera pose predictor, and we just train the generator and discriminator alternatively. Actually, the view sample is important. The view sample actually use the predict camera pose of the real image. Here the view sample, Actually, because we want to match the camera pose, camera pose with so-called the ground truth camera pose in the real image. Although the ground truth is not known, it's not known, but we using the camera pose predictor to extract the current ground truth camera pose, and then we use the camera pose to render the generated image, so we can get some view image on the similar camera pose, and then we ask the discriminator to distribute this two kind of image, which one is real, which one is fake. Yeah. Okay. And in the next stage, we just fix generator, and then we need to train the camera pose predictor. Actually, since our generator can generate a nerve, so we can uniformly sample this nerve from different view and get a get a get a set of images with a known viewport, and we use this information as a supervision to train this camera pose predictor. Actually, for this pre-training, it's just like the regression-based training. Yeah, because we have the ground truth paired data. Because we know the image, we know the viewport. Yeah. So we can just switch this training and until the network converges. So here, due to some team limits, I just keep the network details and just showcase the results. Okay, here are some generation results. Okay, the middle one actually is panorama views, and the left and the right the two perspective views. And this image, this color, this red green, red blue image actually is depth image rendered from the nerve. Yeah, we can see yeah this image, and the next page just shows some dynamic results. Yeah, we just define the camera path and then render the generated things. Yeah. Yeah, the original training dataset only has a low resolution. So our generated result also has a low resolution. So if we can have a more clear and large image data set, probably we can improve our training. Yeah. Okay, we also evaluated the result qualities. We have defined some FID score, and we trained our generation model on different room type separately, and we can see the FID score. Yeah, it's not it's okay actually, although it's not super good. We expect super good means the score is less than 10. Yeah, we also to access scalability of our models, we just change the training data from 5K to 1 million. So we can see the API score actually go low, goes lower along when the training data is bigger. So it means our network actually has a good scalability, and the more to the image for training, we can get a better result. Okay. So we also, because our network can estimate the camera distribution, camera port distribution. So we actually to access all the camera distribution using our camera port predictor. So we can see for the LSAM data, actually we just plot this histogram about the FOV and also this the position of the camera and also the rotation angles within the local coordinate system. But unfortunately, LSAM data don't have the ground truth, so we don't know whether this camera distribution is good or really is really good. So we also did another experience. So we just using the structured 3D images because for all this image we have the ground truth value. So we feed this image to our network, and we can also get the camera pose distributions. So we compare them with the ground truth. Yeah, but for the training, we don't know the ground truth. But after training, we can compare with the ground truth provided by the structured 3D dataset. So you can see actually the red one is ground truth distribution about this value, like the FOV. But we can see, so with small training steps, so actually our results gradually match to the ground truth distribution. So it means for all this image, we also can see the similar effect. You can see that, yeah, this green one is our final result, and this red one is GT. So we can see they are close to each other. So it means our camera distribution estimation is actually did a good job. So here's another comparison. We compared with other indoor sense generation method. For instance, for the depth scan, the EG3D, so you only can generate some 3D scenes within limited angles. And the middle one is we just introduce other camera pose to revise the EG3D, so it can generate the whole things. Yeah, but it still has many limitations. We will show them in the next figure. So we actually from these videos, we also can see some random flashing and the inconsistent image. Yeah, And we also compare the text room with the diffusion-based method using the painting to complete the whole things. Actually, the imagery, the texture looks great, but if we look at the details, actually geometry has a problem, and also the layout is abnormal. So you can see a many bed in a single room. Yeah, but it usually doesn't. It's not real for. It doesn't exist in real things. And the next page, we just illustrate these issues. For instance, for depth scan, blob scan, we just highlight the inconsistent part. For instance, in this frame, you can see the painting looks like the one, and for in the second frame, yeah, the painting is changed. So for all the depth scan, all the blob scan 3D and EG3D, they all have these 3D inconsistent issues. And for the EG3D, so since we revised the EG3D and also texture room, we can see there are still some 3D inconsistency and abnormal layout. For instance, if we look at this room, we can see there's several beds in a single room and close to each other. So we know it's very unusual. Yeah. Okay. So it just showcases so many results, but we still have some limitation. If we just zoom in our result, then we still see many artifacts. For instance, our current approach actually make some assumption. So the room is also has a box like the boundary. Yeah, we currently we didn't support the arbitrary boundary, and also our input training image actually has limited resolution. I have mentioned before, so we expect to using more high resolution image to improve the result. So for our currently result, we still can see some incorrect geometry in our nerve. Yeah, and also our result also has a less ratio of the abnormal layout, but we still can find some unusual layout. So we try to imitate them by providing other prior using other data set. Yeah. Okay, so just to summarize, so we have these general takeaway these messages. So first things from our learning, so we know the 3D data scale really matters. So for strength our 3D learning, we really need to use the lattice set for the network design and validation. And also from our String 3D plus work, we have seen the opportunity to using multi-source data for 3D learning. But here we need to address the domain gap. So we cannot simply merge all this data together for training. So I think there's some potential to using the similar ideas to, to handle the domain gap for utilize the different data set in, I think in the embody AI, but just so because for different the robotics, the data set also has contains so many different domain gaps. How to combine them together? I think we need to design a special strategy to combine them together. Also for the 3D generation, I have shown unified image data actually is good for indoor things generations. But the main challenge is to tackle with labels label insufficient problems. So here we have no camera pose for supervision. So we need to develop a network to simultaneously to predict the camera pose and also generate the 3D scenes. Okay, that's all for my talk. So I would like to thank our collaborators and also our Spin 3D papers are actually published in the CVM journals, and our in the wide image sixth generation actually is under submission. Okay, thank you.
Okay, thank you, Dr. Yang Liu, for the great talk. And here is some questions. Okay, a typical issue with 3D deep learning is the high spatial complexity of 3D data, such as the inability to process the 3D point clouds of large-scale 3D schemes. What do you think is the solution? What do you think is the solution to this problem? Do you think it's a better way to project 3D data to 2D images for understanding 3D?
Yeah, I think yeah, I agree. There's also a lot of work to utilize the 2D 2D image information because we have some large 2D backbone, pre-trained backbone to get effective learning features. And I think there's also a lot of work just combine the 3D feature and the 2D feature together to improve the network. Network. I think it's promising ways because we still cannot get enough large 3D data set. So you utilize 2D image features is necessary.
Okay. And let's thank Dr. Yang Liu again. And the second speaker is Professor Ziwei Liu. Now let me introduce Ziwei Liu. He is currently an assistant professor at Nanyang Technical Universities. His research involves computer vision, machine learning, and computer graphics. He is the recipient of Prime Mark Evelyn Hunt Prize, MIT TR Innovators, and the 35th Asia Pacific SBS Frontiers of Science Award, CPR Best Paper Candidates, and Asian Young Scientist Fellowship. Okay, now let's welcome Ziwei Liu to start his talk.
Okay, so thanks, Scott, for the nice introduction. So can you see my screen now?
Yes, I can.
Okay, that's good. Okay, so today is my great honor to be here. So I would like to share some of my our group's work, very recent work that is from high fidelity 3D generative models to the dynamic embodied learning. And I'm Ziwei. I'm from Nanyang Technology University, Singapore. So I think nowadays, lots of people trying to bring the AI from the digital world to the physical world, right? So in the past 2 years, there's lots of progress that in this 3D and 4D generation, and now people are trying to bring that from this like metaverse to the real verse. That is, how can we enable this learning of agents that can help us to accomplish different real tasks? However, there's one problem, that is how to scale up the data, like Dr. Luan has just introduced, right? So it's not so easy to collect enough data to learn a very good agent for like embodied AI. For other tasks like 2D, they have ImageNet, they have like scaling up all the images, videos on the internet, like the Sora, so it's very good to learn. However, for 3D and for embodied AI, it's always a problem, right? So now I think the idea is how can we like combine the advantage of both, using the generative models to provide simulations for the embodied AI and using the embodied AI as the touchstone that can kind of obtain the supervision signal from the physical world to supervise the generative models to learn better physics, right? So can we enable this kind of very good cycles, that is to learn a very good generative simulator, help us to this embodied learning. I think it's toward this goal of generative simulators. Actually, our group has split different directions so that we can develop different modules and finally can combine them together. Of course, you can see in this case, the first thing we want to understand if we want to build generative simulator is we want to generate pretty good 3D scene. So sometimes it has to be a very, very large scale thing, like outdoor thing, natural thing, urban thing, right? So we want to develop a very principled way to do this 3D generation of the scene. So next, of course, is objects. So actual objects everywhere, so they have different geometries, different appearance, different physics. So I think until today, we still don't have a very satisfying models that can achieve general object generation, right? So I think I will share one of our recent work that tries to enable this PBR asset generations. And beside the scene and object, of course, it's the humans, right? There's humans everywhere. We build generative AI to collaborate with our humans so that we can accomplish certain tasks. So I also introduced how we can enable very realistic 3D human generations that is also animatable and editable. And finally, it's about the motions, right? So for the embodied AI, the motion that matters is about this ego motion. So that is, can we understand kind of the motion signals of the human itself, right? So can I kind of using my own ego motions to accomplish some manipulation task. So how to perceive and understand this ego motion, that's also very important problem. So in summary, actually for this talk, I'm going to introduce 4 aspects. The first is about 3D scene generation. Second, about the 3D object generation, and third is human generation, and fourth is ego motion understanding. It's a attempt in this large models for the ego motions. The thing I will, due to the time limit, I'll just spend quite a few times for each of the topic. If you're interested, I think most of the work that have already been put on archive and also has open source models. So for this 3D scene generations, I will first introduce one of our work. It's called Scene Dreamer, made by my PhD students, Zhao Xi. So it's called Generate Unbounded 3D Scenes from 2D Images. So I think that the motivation is very similar to the previous talk. So that is to enable the generation of the 3D scenes. So first, it's very hard to collect large-scale, real-scan scene dataset, scene level dataset, because it's unlike like the self-driving scenario, right? You can use kind of flips to collect different like street view videos. So for this natural scene, general scenes, it's very hard. So what we have is we have lots of in the wild 2D image collections. From the internet, you can search for like natural scenes, like mountains, like the seas, the islands, lots of them. However, you don't have like the 3D ground truth with a 3D real scanned kind of geometry out there. So how can we use these 2D image collections as the supervision signal, as a data source, to learn an unbounded 3D scene generator? So this generator should have several appealing properties. For example, it should have markedly consistent from different viewpoints, should have very good geometries, right? Like the depth, like the surface, and also should have like diverse scene styles. So that is a kind of a true generative models instead of memorize the data set. So our method, I think it's pretty straightforward. So of course, we first learn BEV scene representation, just like in the self-driving domains that is using this bird eye view, that both is semantic field and height field. Then using these BEV scene representations, we have a generative hash grid. So this hash grid can help us to learn very good large-scale scene generation. And I will talk later, that is, we have compared different representations like hash grid, like triplan, to see which one is better. And finally, we use a volumetric renderer with a GAN step loss so that we can learn from this in the wild image collections. So for the details, I think I will quickly go through. So for the BEV, like both for the height map and for the semantic map, we use the procedural generation, just like how the people, they kind of design the games, right? So for the video games, we use the procedural generation here. For the BEV, we're also following this Bayesian interpolation to synthesize this generation. So after that, we can do in this infinite 3D world because it's a procedural. As you go along the world, you can synthesize like different part of the 3D scenes. And of course, to enable this one, we also, during the inference, we have a sliding windows strategies. You can see for this part, when we go into this part, then we will try to synthesize and doing some blendings in this kind of sliding window boundaries out there. And we can also change different camera trajectories out there. You can see we can sample different styles, like the winter, like the summer, and like the sunrise, right, sunsets. And we can also have different camera trajectories. We have the drone views. You can also have this camera in the street view, right? And of course, we have some experiments. We compare with GAN-based method like GANcraft, AG3D, and also the method that is dedicated for this outdoor scene generation like Infinite Zero. We can see compared to others, we have, of course, have better appearance and also the geometries out there. And we also can enable very good high quality generations that can scale up to 1K because we have the height map, the semantic map, and we can tune kind of a super resolution modules out there. We compare with like infinite nature zeros. It's much better. And to confirm that our model actually generates 3D consistent results, we actually reconstruct camera pose using the structural motion from the render trajectories. You can see the comparisons. Ours is the best, that is close to the ground truth. And you can see we also try this density construction. The kind of the results further confirm that our result is truly have this 3D consistency. So here is the kind of one of the investigation on the key design. That is how to fuse the semantic map, height map using the hyperspace, right? There are lots of ways to enable the scene features. We can use a pure MLP, or you can use MLP with position encoding, hypernet, modulation, triplan, or hash grid. So we can see the results that is for this our scenario, this 3D outdoor scene generation. So I think the hash grid, I think from our experiments is the best in this case. And we can also enable the scale interpolation that should confirm that the model is smooth in the latent space, right? So it's not trying to learn several discrete mode, is indeed very smooth latent space out there. And we can also do in the stylized releasing by control net. We can learn some like the style modulation to making this wonderland. So after that, we are very curious about, okay, we can synthesize very good natural scenes. So how about like city scale, right? So that's why we have built another model. It's called AsiaGraphics. Of course, we have a new one. It's called like the Gaussian city to further accelerate the generation speed. So it's led by my postdoc, Hao Zhe. So I think proposed method from the model perspective is very similar to SceneDreamer. So the real challenge comes from the data. So as I said, it's very hard to collect very large scale and good scene level data set. So for the city scale, we have lots of data set. However, it's very hard to get pale data. The pale data means to have both the layouts and also the appearance, right? So here we have the OpenStreetMap. OSM is also built by us. So it has the real world city layouts, very accurate. However, it don't have very photorealistic appearance. So for these Google Earth, right, you know, the Google Earth, they have lots of real world this city appearance. However, they don't have very accurate city layouts. So we try to build in correspondence on both so that we can learn unbounded city generation that has both these layouts and also the appearance of the 3D cities. So from method itself, I think it has two insights different from this SceneDreamer. The first that for the layout of the city, since it follows certain kind of rules from this urban planning, so it has very significant styles of the plannings inside. So for the semantic map and for the height map, we can actually use a discrete code like VQVAE or VQGAN so that we can kind of enable quantize these two maps into a codebook or the tokens, right? Then after that, we can use this visual token prediction, just like the language model, right? So next token prediction to synthesize both the semantic map and height map. So the first insight. So for this SceneDreamer, for the natural scene, we use this Bayesian interpolation, this procedural generations. However, for the city, since it has very regular patterns, so we use this quantization with the codebook. Then we have another insight that the city should not be seen as a whole. It should be seen a composition of these building instances and the background. So for the background, I mean, it's the road, it's the vegetations, like the rivers out there, right? So for all this background, we can use very similar ways, like a SceneDreamer using this hash grid. However, for the buildings, that is all of the cities, you should follow in the instance level generation, right? So you should treat each building instance as one kind of generation assets, right, to do the generation. So here we use these local encoders for each of the instance. Then we use similar mesh renderer to generate each instance of the building. And finally, we try to combine the city background and the building instance together. And you can see the results. We compare with the precise nature, SceneDreamer, Infinite City. So you can see on ours, we have much better geometries and also the appearance. Okay, so after scene level generations, we switch to the object level generation. So it's a very recent work. It's called 3Topia XL. So it's a 3D PBR asset generations, well, primitive diffusion. It's also led by Toshi. So this work, the motivation is that the current 3D object generation models, I think many of you know the like Dreaming Gaussians or LGM or a lot of like 013. So typically they have low quality of the geometries. And since many of the model nowadays, they are reconstruction based since the large LRM, right? So they are deterministic. They are not the true generative models. And the third is that they are only generates the geometries and appearance. So they have no PBR. It's a physics-based rendering, so no physics. So when you put the 3D assets in a new scenes, you can't do this relighting and other renderings, right? So it's not good. So in this project, we aim for high quality geometries to be quite smooth and regularized. Second is the 3D native 3D models. That is, it is true geometry models, learn from 3D data and can generate 3D data and can do some samplings inside. And finally is that we want to enable this PBR asset generation. So it should have the correct physics. So here is one of the results from one single image or one single text prompt. We can generate a PBR asset. So this asset is really high quality enough and ready for rendering in the Blender. You can see we also have this metallic roughness, this PBR modeling of the materials. So our key idea is use the so-called primitive diffusions, right? So many of you knows that I think the key problem in 3D is the representations. It's always representations. So for the 3D thing, we figure out, okay, the representation should be the hash grid. However, for the kind of the 3D objects, we actually have tried different ways. At first, we have tried the triplan. So that is the 3Dtopia 1.0 version 1. So for this version 2, we switched to another representation. So that tries to combining the advantage of these point-wise representations and also this neural field. It's called primitive diffusion. So what's primitives? So here we define this, you can see, given one GRB mesh, so it has the geometry of the texture of the materials. So one primitive, this one was defined as SDF primitives. So it is consists of first is its position, 3D position. It's called 3D anchors. Then it's SDF to represent these geometries. It's 8 by 8 bytes. Then we also have this RGB, this appearance. It's 8 by 8 by 3. Then we have these materials that to model in the PBR materials. It's 8 by 8 by 2. And finally, the scale, right? This scale factor. It's only a scalar. So combining them together, we have this primitive is n by d, right? Because it's n by d, and it's the total number of primitives, and d is dimension of these primitives. So it's 3 plus 8 to 3 times 6 plus 1. So we actually use these n by d tensors to represent a textured mesh. So actually find this very efficient. So just within 1 minute, you can feed this GRB mesh into our primitive representations. You can also try others, like I think in the paper we have compared with like triplan and other very popular implementations. So we show that this primitives has its own unique advantages out there. So I think the following is very standard. We just follow like the Thora-like approach. First train a VAE. However, for the 3D, we doing this patchwise compression. So we compress these primitives using encoder and decoder to the 3D latents. Then we use the DIT, the diffusion transformers, right, to operate on these 3D latents. So we scale up this DIT to 1 billion parameters to truly enable 3D foundation models. And actually, we use kind of a subset, a high quality subset of this Omni Object 3D and some of our own collected this Omni Object 3D dataset. So it's 200K data, this object verse and Omni Object 3D. Right? So, okay, so using this 1 billion models and this 200K data, we can already learn very good results. We can do this denoising in just 5 seconds. So it's a feed-forward model, no optimization involved. So of course, you can use this one combined with other methods. So currently, there's lots of methods using kind of post-processing with this SDS or other method. So our can definitely serve as an initialization. So it's also ready for rendering engines. You can see when put into different these HDR environments, this can do decent relightance. Of course, it's not perfect yet, so we can using our framework to do further scaling, of course, if you have your own high quality data. And you can see the comparisons with Instant Mesh, with Real 3D, CM, Craftsman, Shapey, and ours. So compare the geometry and also the PBR materials. So we have some advantage out there. And you can also see our is the true generative models. So given the same text prompt with the same image prompt, we can have different results, different metallic, different roughness. So we have some certain stochastic inside these generative models. So the third is about the human generations. So here we want to introduce our recent work. It's called Struct LBM, just presented in the recent ECCB 2024. So it's led by my postdoc, Utao. And I think many of you actually know the background of the field, right? So since this AG3D and FS3D, so lots of people trying to enable the 3D human generations, this photorealistic generations out there. So they usually following this pipeline that is to trying to map this kind of appearance and sampling on these 3D human parametric models and using a GAN models, GAN loss, right, or a GAN framework. So actually, if we see the progress from this iClear 2023 of the MS3D is also from our group, and to this CPR 2024, this GAN-based method, actually our group have also tried to scale up. It's very hard, right? Very hard. So this photorealistic 3D human GAN is very hard to train, actually given this heterogeneous data sources. Because for 3D humans, we certainly have lots of 2D image collections. We also have lots of like 2D videos, human videos. We also have like decent amount of 3D humans. Like how to leverage different data sources. If you use a GAN model, it becomes pretty hard from our experience, right, to train. So we're thinking of, okay, how about building a diffusion model, right? Just like the stable diffusions. So using a large amount of human data set and with certain human representations, we train a LDM, right, latent diffusion model, then that's solved. So the problem becomes how to design this human representation. So that's again, come back to the scene that is I said. So 3D representations are key. So for the scene, for the objects, for the humans, you should choose different representations. So this representation first, it should be expressive enough for this high fidelity 3D human reconstruction, right? So it should have this capability. The second is it should be compact enough for efficient diffusion model training. So it shouldn't be a very high dimensional thing. It should be structured, right? So if we consider both requirements, so we propose 2D structured latent representations. So because most purpose work, they just use the 1D representations or 1D embeddings as the latent. So here we propose using a 2D structured latent that has also the UV map modeling inside. So here, then from this 1D latent space to this 2D structured latent space, I think that's the key insights of this work, right? The previous work like FS3D is always from 1D latent space, and here we jump to this 2D structured latent space. It has several like appealing properties. Of course, with 2D, it enables easy local editing because you already have the 2D latents. You can directly operate on the latents, right? So with these latent representations, then we can do the queries, we can integrate the features. If you need like high resolution results, like from 500 by 500 to 1K, you can build in some SR modules. And finally, you can learn autodecoder, right, to learn this latent space. For the latent space, we have the render and SR is trainable, and you can have the supervision from both appearance, this photometric loss, and also this geometric loss, because it has the ground truth image and the parametric models, right? We have two loss functions, reconstruction loss, and adversarial loss. Then you can learn from 2D image collections, monocular human videos, and 3D human data set, right? You can leverage essentially all the data sources for the 3D humans. And you can see the results, it's pretty decent. So compare with the GAN-based method, it's pretty good. So primitive diffusion is another diffusion-based method for 3D human. It's also from Joshi. So compare with both GAN and diffusion, so our method is pretty unique advantage that is can perform well in the well 2D images. So for the UBC fashion, it's 2D video data sets. Render people is 3D, right? So you can see it can do pretty good. So you can see the comparison of the geometries, appearance, even from the back and different poses. It's pretty good. And can also do controllable 3D image generations, as I said, because we just use this 2D latent. You can control the pose, you can control the shape, you can also do the interpolations. You can even do this mixing, right, composition. For example, I want the color of this clothing, and I want this sleeve of this one, on the shoe of this one, so can I combine them together? So the answer is yes, because you can combine these 2D latent features, right? So that's good. So after this work, we actually are also thinking how to move forward for the 3D human kind of generative models. The first is this autodecoder is actually bottleneck. It's kind of determine the upper bound of the quality. So how to train a better autodecoder, definitely one way. Another is the loose clothing. It's also one of the challenge. So I think from the previous data sets, they don't have lots of these loose clothings. Of course, there's lots of newly collected data sets like BA rendering. They have this loose clothing. So that's definitely one aspect to improve. And finally, is to further sculpt for the sculpt. I think to collect human data from this lab setting using like mocap, it's always not scaled enough, right? Because we have lots of videos like in the 2D. So how can we enable this leverage of the in-the-wild 2D videos for 3D FDG creation? So we have a recent attempts. It's called the wild avatar. So we try to kind of bridge the gap and try to establish a data pipeline that can extract 3D humans from this in-the-wild 2D video data set. So after I produce the 3D scenes, 3D objects, 3D humans, they are still static, right? So we can't understand this dynamic world, world's dynamic or human dynamic, our actions dynamic, right? So how to understand this eco motion? This work is called Eco LM. It's led by my PhD Fangzhou. So it's also collaborated with the Meta Red Lab. So I think the background of the motivation is also straightforward. Nowadays, we have very brilliant these multi-model large language models like GPT-4o or the recent one. So however, even though they're very good at read image, read text, or good at this chat, they can't understand the egocentric motions. So egocentric motions, they can actually are very critical for understanding our human behaviors, right? So what we want to do and what is our social events, right? It's very important. However, the current large language model can't do that. So our kind of motivation that using the current setting of this egocentric capture, for example, with these sparse motion sensors, you're just wearing an AI glass. If you see this recent release of Meta ribbon, right? You have the AI glass. Maybe you have some like the another two sensors on your wrist, and you see some egocentric videos like the AI glass. You also get some molecular videos. So just with these molecular videos and also very sparse sensors of the motion, so can we do two things? That is the 3D points body tracking and also understanding, right? So these are all individual tasks in the field in the egocentric motion understanding. That is firstly trying to do the tracking, just given the 3 points, the head and 2 hands, right? Or just given 1 point and just the head. So they want to reconstruct 3D human bodies. So another task they're quite trying to do is to do the QA, like Ego 40 or like Ego test QA. So given one molecular videos, they want to understand the actions, the objects, and also the rationales of the events inside, right? So there are two kind of separate tasks in the field nowadays, is egocentric understanding or egocentric tracking. So our motivation is that can we use the kind of synergy of this motion language so that we building a unified model with one single model that takes the impulse of the sparse sensors of the molecular videos, and we can do both motion tracking and motion understanding. So I think our paper or our project confirmed that it is true, right? Using one language model, we can do both. We can do this motion understanding, this QA, and also this dynamic understanding, this motion tracking. So for this multi-model, multitasking language model for ego motions, I think we're following a very standard way, like how Meta they built the llama, right? So we use the same. So the first thing to do is do the tokenization, right? No matter you are doing language models, you are doing like video multimodality models, first thing is do the tokenization. So here refers to learn a very good motion V2VAE for these ego motions. Second is that we should do some motion pre-training, just like people pre-train the language models. We should kind of synchronize these motion tokens so that the language models can see the motions as a new language. And finally, we try to bringing all the sources together, like the encoders for the sparse sensors, encoders for the videos, and this natural language instructions, so that our models can do both. It's called instruction tuning, right? Just like language models, first do the tokenizations, then do the pre-training, and finally do the instruction tuning. So I think I will skip the details So for the motion vehicle VAE, we find that we should do this it's called product quantization. We should use 2 code books instead of 1, right? So that's our key insight. If you're interested, you can look at the paper. And for the pre-training part, I think they are very much like the language models. We're doing the tokens using the next token predictions to train this one. We of course have a vocabulary. We try to expand this vocabulary so that it can understand the motions within the cross entropys to kind of to do the prediction. So one byproduct is with this motion pre-training on the language models, we actually got these unconditional motion generators. You can see we can sampling from these language models. It tries to accomplish different daily activities on our humans, right? So it's kind of byproducts. We also learn some motion generations. And the third step is function tuning. So of course we try to doing different tokenizations, text tokenization, video tokenization, this 3 points, this sparse sensor tokenization together. We'll concatenate all the tokens together, fit into this language model. It's you can use GPT, or you can use Llama, then that's done, right? The experiment says, does it work, right? So because we're trying to unify the field, we try to accomplish both 3D dynamic learning of this body tracking and also the QA, like the very high level task and very low level task. So the question, does it work? The second is this multimodal helps because we trying to incorporate the sparse sensors, the language, the videos, right? So some of them are 1D signals, some of them are 2D signals, some of them are 3D signals. So whether we combining the different like modality together help. So our experiments confirm both. So yes, right? So does it work? The answer is yes. Here's demo videos, right? So it's a kind of real world, this meta aerial glass. So we use these egocentric videos. You can see it can track the motions pretty well and can understand so what the person is trying to do and what are the surroundings or the scenarios, right? So it actually works pretty well and has a nice generalization ability. And of course, there's more experiments that showing the multimodality really help. If you're interested, you can check the paper that will show that combining the 3 different modalities can help each other, right? So with the 3 points, you can help also with the video and language understandings. With the video and language, you can also help with this body tracking. So move forward. Of course, the first thing to do is to scale up. We want to build larger language models. I think for this one, so our kind of this model size is like GPT-2. Of course, we can scale up to GPT-3 and GPT-4. And second is that the egocentric video encoding, we can do better. So here we use a very nice way, just like the clip. So of course, you can use the nowadays like the lava videos, right, to do this video encoding. And finally is to incorporate more modalities and more tasks into this one. Because for egocentric, you have lots of tasks besides this understanding more body movements and also these Q understandings. You can also enable other embodied AI tasks like manipulations, right? Like human-human interactions into our models. So that's our future directions. So in summary, our current progress is for these generative simulators, we have pretty good generative models for 3D scenes, 3D objects that can be put into scenes because of PBR, 3D humans, and this ego motion understanding, this language model. In the future, so we want to further pursue these physical properties because we want to bridge the gap of the digital world and the physical world. So one aspect is about how to do battery lighting. So that it's more realistic when we put the object humans into the scenes. The second is more about the physical properties, so how the dynamics of physics and also the materials to better. So that, and finally, we can build in these generative simulators for this embodied AI learning. And I think most of the works, all of the works, they have been put on the archive, and most of them are open source. If you're interested, you can check out our paper, our code, and model you can play. Right? If you have any questions, feel free to ask me. I think that's all for my talk, and thank you for today's time. Yeah.
Okay, thanks for the great talk. And here are 2 questions.
Yeah.
The first one, do you think it's better to work on 3D generation directly in 3D or to use 2D video generative models for 3D generation?
Okay, I think that's a very good question. So I think nowadays there's two directions. The first direction is to leverage the current very powerful 2D models like Stable Diffusions or the current video diffusion models, SVD, or if some like the Coq videos, right? So in my opinions, they should be combined together. So here you can see in our talk, for these 3D object generations, we just use this 3D data. And for others, for the scene generations, we use like the 2D images. So in my view, so the video diffusion models or image diffusion models, they kind of provide different supervision signals than the 3D ground truth itself. So 3D ground truth is very good for learning these primitives, how to do the computation, how to do the geometries. However, for the appearance or when this object is combining with other like objects or scenes, it can't do quite well. However, current video diffusion models, I think, because our groups are also doing this video diffusion, they can learn pretty nice composition and pretty nice this kind of this camera movement. So the caveat or the drawback of the video diffusion models is that they don't have the 3D consistency. If you move the kind of the camera, the viewpoint to an extreme angle. So I think the future is how to combine both. So I believe that's the way.
Okay. And the second question is, currently the progress of 3D generation is very impressive. What do you think are there still some promising research points in the 3D generation?
Okay, so I think that's also a wonderful question. I think there's two different kind of levels for thinking. The first is for the task itself. I think for the 3D scene, 3D objects, 3D human, already lots of works inside. So I think the first, from the task perspective, point one, you can go for like the interaction, right? So we have very good models on scene, object, and humans. However, for the human object interaction, we don't have very good models, right? So can you have general models of very good human object interaction or human scene or like others, right? How to combine the three. So that's the key. So we already have some works. However, I think they're pretty primitives, right? We should have pretty much room to improve. And the second level is on this model design. I think for the 3D human, they are very close to the industrial usage. They have lots of very good designs on the presentations. I think for humans, I will suggest just go for real usage, right? You just think of a very real world problem and try to kind of accomplish your good system for that. And from that, you can figure out a good research direction. And for these two, for 3D scene and 3D objects, I think 3D object is kind of hindered by the scale of the dataset. So even though we have the objectverse or Omniverse 3D, so they are still pretty small. Objectverse, they are quite noisy. So if you filter out the high quality data is not enough. So how can we scale up the 3D object level data? For example, using video data, I think that's the way. And for 3D scene, I think still much room to go. So even though I showed the scene dreamer and stage dreamer, the representation itself still need to improve, right? So how can we deliver the true, like the digital twin of the city, right? I think that's still needs very good progress in the geometry modeling and appearance modeling. So from both task-wise and also model-wise, I think we have lots of exciting direction to explore.
Okay, very cool. Okay, and thanks for Professor Zui again. And our online seminar is here. Bye, everyone.
Yeah, thank you. Bye.
Bye.